Marina. We'll get started with B to the 4. BC, bark, BioInnovation at BPI. That was my invention. 4 times B. Anyway.
I have a mic here.
Yes.
Perfect. Okay, so this is the list of speakers today, but I want to start with this picture of Pacific Spirit Park, just to take an appreciation of the land that we live on here. Being from Phoenix, Arizona, I'm from a desert climate, and so seeing these trees is actually a very new landscape for me. And so today I'll be talking about my work using Western hemlock bark for clean water. And here on the background of this slide, this is actually a photo I found of Uchucklesaht traditional territory. And so I really wanted to show where this bark is coming from. This is bark that Dave sent me, and so I'm really grateful to work with it. Holding the bark, I honestly had such a strong response from it because I think it's really such a beautiful example of how nature lives together. You can see the ridges in the bark from where beetles have buried in it. Some of the bark pieces had lichen or moss growing on the outside. And so what's really special about this bark is that it is harvested part of forestry management and doesn't compromise the life of standing trees. And so what we aim to do is valorize this bark residual to not only promote circularity in the forest resources, but also to safeguard our waters in Canada by finding ways to clean our water. And so what we know about this bark is that it contains tannins. And so tannins can constitute up to 15.5% by mass of Western hemlock bark. And what these tannins are is essentially an array of these very polyphenolic compounds that have different structures depending on what kind of biomass that you're looking at. And these are tannins. And so you might actually already be familiar with tannins. So if you've ever gone red wine tasting, they'll often talk about the tannin profile because tannins are prevalent in grapes. They're prevalent in the oak barrels that the wine is fermented in. And Isabella will talk more about this today. And so tannins are edible. And they actually are used to tan leather, and that's where the name comes from, tannin, tannins. And so we know that they have a very strong interaction with proteins in animal hides to give it this color. But you probably didn't know that they can clean water. And so I'll talk about 2 initiatives that we've done here at BPI very quickly on how we've demonstrated that tannins can clean water. And one is in maybe an unexpected place. So this is a poultry farm. And typically in poultry farms, especially of this size where there's so many chickens in one place, they have to be given some kind of antibiotics to prevent disease from spreading. And so in collaboration with Professor John Linguo, who did a sabbatical here in BPI, as well as Yu Wang, we essentially decided that we could potentially remove the antibiotics from the poultry effluents before they're released into the environment by using tannins. And how we did that is taking a commercial polyamide filter. So this is something that was already being used to treat water. However, these filters couldn't remove antibiotics alone. And what was done is we added tannins to the filter. And in order to keep the tannins there so they didn't just run off, we coordinated them with ferric ions. And this facilitates tannin coordination so that they stay in the filter. And when the filters had these tannins, we found that they were able to remove over 98% of antibiotics from these poultry effluents. And we actually tested real poultry effluents from real poultry farms in China. And these effluents contain 9 diverse antibiotics. And we also found that these filters could be regenerable with a mild acidic wash because if we reduce the pH below 5.5, the tannins will run off with the antibiotics and then the filter can be regenerated. Another issue we looked at is the plastic problem. So microplastics and nanoplastics are found virtually everywhere. They're in our oceans, they're in our rivers, people are finding them in rain droplets even, they're in our meat, they're in our vegetables, and they're even inside of us. So one of my most famous alarming statistics that I love to give out is that every single person in this room has about a credit card size worth of microplastics accumulated in them. And while we don't quite understand the long-term effects of microplastic pollution inside of us, we do know that it causes inflammation and has been associated with heightened cancer risks. And so the question became, should we fight plastics with more plastic? So in the last work, we used a polyamide filter, which is a synthetic material. So should we do the same thing again? Should we take a synthetic material, coat it with tannins, and then remove microplastics and nanoplastics from water? But to be honest, that filter is also probably contributing to plastic pollution because it is a plastic as well. So we decided to just completely scratch that and start from something new, starting with forestry materials. So we actually took wood processing waste from a sawmill to serve as the new substrate for the filter rather than the polyamide. And then we also used tannin extract. And we essentially coordinated the tannins onto this sawmill waste, which is here in this tube. So this is a simple water filter. The water will drip through the tube, and the tannins are collecting microplastics and nanoplastics by absorption-based capture. And this is important because typically microplastics and nanoplastics are just too small to be filtered out by size. So that's why it has to be by absorption. And we found that this filter can remove over 95% of microplastics and nanoplastics from water. And I'll break down this work a bit more. So we tested the 6 most common polluting plastic species. We looked at polyester. This one is particularly egregious because it's in all of our clothes, our laundry. And we tested a range of particles and found that we could remove 99.8% of them. We looked at polyethylene, which has a neutral charge and is typically found in your grocery bags. This is actually the lowest removal percentage. We also looked at polystyrene, and we looked at both negative and positively charged forms of polystyrene, as well as polypropylene, which is common in Tupperware. So this one is going through your dishwasher drain all the time if you put your Tupperware in there. We also looked at PMMA, as well as polyvinyl chloride, or PVC. And as you can see, all of our removal rates are above 95%. So you might be wondering, okay, this is really cool, but why are tannins doing this? And so just as a summary, these are basically all of the compounds that we looked at in these studies, and you can probably appreciate that they have very different chemical structures. Some of them are positively charged, some of them are negatively charged, and they also carry very different properties. But what's really unique about tannins is that they can facilitate a diversity of intermolecular interactions, and they only need one of these to work to absorb a compound. But for many of these cases, they're using more than one. So they're using either hydrophobic interactions, such as the compounds that are highlighted in blue, electrostatic interactions, hydrogen bonding, or pi-pi interactions to capture these molecules as a whole. And so I guess my main message that I want to leave with today is that the innovation needed to clean our water can start in forestry. Rather than thinking about all these polyamide filters or other plastic-based resins, I do think there's equal value in looking how forestry resources can be used for these advanced applications. And so for our future work, I'm really happy to be working with the Uchucklesaht tribe and the Ministry of Forests to be able to expand the potential of tannins by further investigating their role and ability to remove other pollutants from water, specifically ones that are present here in Canada. Thank you.
Thank you, Marina. Can I ask Isabel to come up? Oh, no, Gio first, right? Sorry, Gio. Good. Yes.
Hello, everyone. So I'm Gio, and I'm working on Western Red Cedar. Here in this presentation, I will show what work has been done, not necessarily here in BPI, but in literature, what we know about Western Red Cedar, its heartwood and in its bark, and is there any potential for us to utilize this resource, or should we even invest in this resource? So a lot of what we know with Western Red Cedar comes from its heartwood, because these researchers from Western Forest Products Laboratory, or they called now BioInnovations, they have extracted these unique phytochemicals from the heartwood, and some of these chemicals have been named after the tree, and they have been patented already for use in pharmaceuticals and in food. But there is little that they know about the components of the bark. But what they know is that they have very low. The extractives in bark are very low in concentration, as if you compare them with the heartwood. But so what they have tried are different types of extractions. So they use different polarities, starting from the nonpolar from the top, going to increasing polarity to the bottom. So they use petroleum ether, and all of these have a lot of fractionations after them, but they found out very small amounts of these active biomolecules, so they have a lot of bioactivities. In ethanol, they have found an interesting group of compounds called flavophines, which I will discuss in the next slide. In methanol, there are a lot of chemicals, but they are not unique to Western Red Cedar. And when they used water, they extracted a lot of polyflavonoids and a lot of polysaccharides. So I will touch upon the polysaccharides and the flavophines. So these flavonoids are highly polyphenolic, but unlike its water-soluble counterpart, because of their high amount of fused rings, they are water-insoluble, so they can act or they can be dissolved in fat with their fatty acid esters and do their activities in the fatty phase, so in the oil phase. And they have about 4 to 5% in the bark, as they have extracted a heterogeneous mixture. The next one is on non-cellulosic polysaccharides. They have done studies on the woody part, and they contain the arabinosilans and the galactoglucomanans. But in the bark, we don't know yet. So for further research, there is no major component that predominates in Western red cedar bark that might be exploitable as of yet as a commercial chemical. But I do think that advancement of fundamental work on bark chemistry is a necessary groundwork so that utilization of the bark can be made. And then the new knowledge can only be useful in improving cedar bark utilization. Thank you.
Hello, my name is Isabella, and I'm an undergraduate student, and I work primarily with Marina at BPI. So today I'm going to talk about tannins from other botanical sources. So I'll talk about tannins from grapes in the context of red wine bacterial cellulose. So just as a little introduction, I have the structure of a grape. We have the leaf, the stem, which contains some polyphenols, the seed, which also contains some, the pulp, very similar to wood pulp, and then the skin, which is the primary source of anthocyanins, which is tannin, and flavonols, which are aromatic compounds that are antioxidants. So the skin of a grape is very characteristic. So different wines based on the skin will have different characteristics. For example, in red wine, the astringent, bitter flavor that dries your mouth out comes from the tannins. So the purpose of my research is to take red wine and ferment it. And a natural byproduct of this fermentation is bacterial cellulose. So at the liquid and oxygen interface, we get a film that you can pick up, and that's all bacterial cellulose. And we can treat this cellulose to form a bioplastic with applications in food packaging. So this is an industrial waste product where an estimated 3 million kilograms of bacterial cellulose are produced in the red wine vinegar industry annually and thrown out. The purpose of my research is to repurpose this bacterial cellulose by adding value to it. So we can capitalize on the antioxidant and antimicrobial properties of tannins for food packaging applications. So for those of you who don't know about bacterial cellulose, I'll introduce it. If you've ever read a paper about cellulose, you know it's the most abundant biopolymer. But bacterial cellulose is a little bit different. So when we have an acetic acid bacteria that we add to growth media and ferment, in the case of red wine, for 14 to 21 days, we get this unique film that's ultra pure and strong. So bacterial cellulose is better than plastic because it's biodegradable and biocompatible. This means it's often used for wound suturing, and then it's better than plant cellulose, in my opinion, because it's pure and stable and exhibits higher crystallinity, permeability, and tensile strength. So this is some SEM images that show up close the structure of bacterial cellulose. So on the far left there, this is traditional growth media that shows a more ordered structure. And then we have bacterial cellulose supplemented with tannin and then from red wine. And you can see from these images that the tannin provides a bit more of a disordered structure, which means that it inhibits growth a bit, but it does possess the unique properties that we want to use. And you can see that's a bacterial cell, and it's sort of actively extruding cellulose there. And these are the polyphenols, so the tannins. So my research treats these films to form a bioplastic. So we start with that red film that we take right out of the media. We cross-link it at 0.1 molar iron chloride. So the purpose of cross-linking is to make sure that the tannins that are only electrostatically bound are kept onto the surface. That's indicated complete by a color change. Then we hot press it at 110 degrees. This improves the surface homogeneity and dehydrates it. dehydrates it, slightly, so that when we plasticize it, we can get uptake of low concentrations of PEG or glycerol. And then we test the tensile strength and contact angle and verify antimicrobial and antioxidant activity. So that cross-linking step is driven by metal ions and pH, making it a two-step process. So we add sodium hydroxide. As the pH increases, we note a color change, and the iron chloride is complexed, so we know our tannins that are on the surface are staying there, and the other tannins are grown into the layers of bacterial cellulose. So overall, the tannins possess desirable properties for food packaging applications. This is a current final film that we have, and initial results demonstrate that we have comparable tensile strength to other bioplastics, but a low hydrophobicity. So a next step for my research is looking at a hydrophobic coating that's bio-based to make these commercially viable. But overall, we've successfully treated an existing waste product to promote a circular bioeconomy. Thank you.
Hi, everyone. So we've previously seen all the work that has been done for valorizing tannins, Western hemlock, and all these other materials. So now we'll be moving on to another type of valorization effort that we've been looking into, and that is valorizing triterpenes from birch bark. So as we know, birch trees are a very popular source for pulp and paper mills, and as a result of the debarking process, a lot of bark waste can be produced, and this can account for up to 40 tons of bark waste produced daily that is either thrown out or used for cheaper fuels. Yet, this can be a potential side stream for a variety of valuable extractives, such as betulin, and this can result in up to 5 tons produced on a daily basis. So what makes betulin a very promising material? First, it is an abundant, naturally occurring lupine-type triterpenoid that is found in the outer bark of birch trees. And it accounts for 20 to 30% of birch bark dry weight, meaning we can extract a lot of this compound and make a lot of use for it in applications. Next, you can see through this extraction process, it is relatively simple to obtain betulin. And this usually involves boiling ethanol for a very short period of time. And lastly, we can see that from the functional groups, it is a very hydrophobic structure, and this can allow it to form very unique supramolecular structures in organic solvents through self-assembly. I'll show one such self-assembly here, where it can be able to form fiber-like self-assemblies that can lead to the formation of a special class of gels called low molecular weight gelators. So here we start off with betulin molecules that are dispersed in an organic solvent of choice, and by just changing the type of concentration and the type of solvent that we use, we're able to obtain these micron scale fibrils. By adding a certain type of trigger, such as heat, now we're able to form a certain type of gel called a low molecular weight gelator. And these gelators are different from your typical polymeric gels in that they are typically weaker in nature and governed by non-covalent interactions. This can allow it to have other properties such as thermal reversibility, allowing it to return back into microfibrils, and it can expand its type of applications. I'll show here, this is one such of this type of gel that we produced and the fiber-like morphology. So this is betulin produced in isopropyl mirror state at 3 weight percent. And you can see all these different types of heterogeneous type of fiber-like morphologies that is produced in this dispersion. And you can see that at around 3 weight percent, we're able to achieve the minimum gelation concentration where the solution is no longer able to flow when inverted in a vial. This is what we call the minimum gelation concentration. And this is typical for a lot of low molecular weight gelators that are able to achieve very low weight percents, usually far below 10 weight percents. So this is just one of many types of morphologies that we're able to produce with betulin. We can also produce these other ones depending on these the organic solvent that we use and also the type of concentration. So I'll also showcase the diverse portfolio that we've been able to create in our lab. First, in chloroform, you can go from these micron scale particles into fiber length morphologies. You get these flower-like micron scale formations in ethyl acetates. Meanwhile, you start off with like a biconcave type platelet morphology at lower concentration, evolving into these very nicely crystalline rhombohedral morphologies at higher concentrations. We get a very nice intertangled yarn-like morphology in 1,2-dichloroethane. And finally, we get these uniform nanoparticles that can be produced by switching our solvent to ethanol. So now, given all this diverse portfolio of our Betulin self-assemblies, we can work towards tailoring our each self-assembly towards unique applications. For instance, these fiber-like morphologies can be used for the encapsulation of gels and for drug loading. Meanwhile, by achieving high aspect ratio and high surface area particles, we can use it as a superhydrophobic coating. Finally, Betulin, having a lot of therapeutic properties, can be used itself as a drug delivery agent for pharmaceutical applications. And now I'll hand the mic over to Shun, who will be talking about these applications in more detail. Thank you.
Hello everyone, from here I would like to give 2 demos about how we use Betulin and to produce some real bioproducts that we can use in daily life. So one example I will raise up here is when we put a dissolved Betulin as an organic phase and then put as water as a outer phase, and we can see clearly with time increase, there is a skin formed on the surface that can easily stable the both phase. So based on this observation, we emulsify the immeasurable liquid, like oil containing Betulin and water. After emulsification, we can get an emulsion system that is a stable, like one-phase system, and made some like Betulin creams used as skincare products that can transfer like the natural power, like protect against the sun and antioxidant functions. And another demo I would like to show here is some porous materials. Like we can easily see that polyurethane is used almost everywhere in our daily life. It with a lot of benefits, like it's cost effective and also like energy efficient, that we can get multi-functions from the polyurethane foam. But currently, there are some concerns related to its use. So firstly, even though the polyurethane linkage is chemically reversible, but currently it's still hard to fully recycle it. And also during the synthesis of the polyurethanes, like the isocyanate polyols are toxic to our human. And also because the polyurethane foam is flammable, so in real case, when it catch the fire, it will release heavy smoke. So that's why in European unions, they have banned the polyurethane foam. So as us, we from the Bioproducts Institute, we try to find sustainable green solutions to replace the polyurethane foam. So what we do first is to get some porous structures as a matrix. So we use foam forming process as the illustration show here, that we first generate some air bubbles, and these air bubbles are wrapped by cellulose fiber, and simply by air drying that we can get a cellulose fiber foam. And as we see, sorry, I'm trying to show the video not play, sorry. Sorry. So sorry. Yeah. No. Yeah. No.
Maybe the video is not playing.
Yes.
Let's try here. Let me just do it. Doesn't matter.
Yeah, but.
Sorry for that.
Yeah, but in this case, we want to show that this scale up, this process can be easily scaled up in a pulp mill. Like, because we use air bubble to reduce the amount of water use. But for cellulose itself is hydrophilic in nature, that if we want to get multi-functions of this foam, it's hard. So this reminds us of the function of Betulin have, as is the protection function of the tree. So we try to add betulin as additives to the foam. And because it's hydrophobic and have poor compatibility with cellulose foam, so here we add one step, that is by polyurethane grafting. So in these 3 steps, we can get 3 different forms. So from the left to right, that we have cellulose foam and polyurethane grafted foam, and the final products is betulin coated foam. So if we find like the betulin coating is fully covered the cellulose surface, and it makes the foam to change from white to an off-white color appearance. But what other function betulin bring? So because we know cellulose foam is easily combusted, like when we put the cellulose foam and the fire, it easily burned within 10 seconds and only left some carbon residues. But after betulin coating, we found that the fire won't spread from the foam, and it self-extinguished within 10 seconds. So that's to say the betulin coating make the foam to be fire resistant. And continue our characterization on our foam. Because we know cellulose is a biopolymer, so we don't want a foam that we made for our wall or the roof degrade maybe 1 month later or 3 months later. So we need enhanced durability. To stimulate this case, we put a cellulose foam and our betulin-coated foam to moisture soil conditions. And with time increase, we can see clearly that the cellulose foam, there are some fungi grow on the surface, and it starts to shrinkage. And after 100 days, it degrades. But for the cellulose, for the betulin-coated foam, the surface is keep fresh. So we can have increased durability of this kind of foam. Now continue our work because we want a replacement for polyurethane foam. So we compare our result in terms of sustainability, antimicrobial, hydrophobicity, lightweight, fire resistant, and thermal insulation properties, and plot firstly show the result of flexible polyurethane foam and rigid polyurethane foam. And we also compared some bio-based foam like cellulose foam, or some reported results that from the lignin-based polyurethane foam. So overall, we see our betulin-coated foam stand out in most of these 6 categories. So from this result, we can conclude that we first designed the emulsions from betulin that can easily stabilize the liquid-liquid interface. And in another demo that we got eco-home materials that with multifunctions, which is super hydrophobic, anti-mold, thermal insulation with extended durability and fire resistance. Thank you.
Super, Sean, thank you. You can take all the questions now.